So being that in this blue line, I have included all of this information. I'm just going to get rid of it now, but you can see where I formed it. It's so important to do the logic to see why this is the case. Now, what do I do with this thing? Have a look at where you're headed, because thankfully this is a proof question, right? Now, this is where I'm meant to end, but that's very obscure. And clearly they're going to use this original part here, okay? So I'm kind of going to go from here to here, to here, to here, okay? I might even jot that down, right? Here is my first step. I'm going to go, because this is a sum of things that look like this, so this will be step 2, so this will be step 3, and then this is where I will end. Okay, great. Now, how can we work with this silly looking thing? The first thing I'm going to do is, notice how the things are progressing from left to right, okay? So you've got 2 bits that are changing. You've got the NCR notation, that's going up, 0, 2, 4, 6. And then you've got the powers, which are going down, which is kind of a problem when we're doing sigma notation, right? We want them both to go up at the same time or go down at the same time. So which is the easiest to change? And the answer is, well, hold on, NCR notation, because it comes from Pascal's triangle, you've got this symmetry, right? So you've got dot, 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 n choose naught on one end and n choose n, of course, are the same, it's symmetrical, okay? So if I note that, then I can actually reverse this whole order. I can reverse all of them. So I'll make this one here, I'll make that n choose n. And this is already an n, that's fine. This will be n minus 2. And so now you can see well, it's not a denominator, but this number down the bottom is matching my power, which is really good. And that's going to be where I'm headed, okay? Because this matches this. Okay? So I'll just finish writing that out. Yeah. Okay, that's good. Now, remember, this is a show question, right? So you've got to make sure you don't skip any steps as you go there. This here is in the wrong order. Right? It's descending, yeah? So really what I should have is this is my start point, okay? You might be able to get away with skipping this line, but I don't think it's a very good idea being that this is a foregone conclusion. So I want to make it super obvious that I understand where the sigma notation's growing out of. So I'm gonna reverse the whole thing, okay? So I've got this. So this would be 2. 3 gets you the pattern. Whoops, sorry, 4. The third term, but it's 4. And the 4.
2 to the 4.
Sorry. too many letters. And then here's my endpoint. Right? So n choose n. And I already said that's 2. Get rid of this so we don't confuse ourselves. Okay. Now I'm ready to put it into sigma notation. Okay. So this is going to be equal to, right. Now what have we got? Well, they've chosen k, so why not? Okay, k equals, and I do start with 0. Okay. Where do I go up to? Right. Well, because things are doubling, right? Things are doubling. That's why I go to n on 2. You don't need to justify that anymore because I've written it out in a super clear way. It's clear enough, I think, that there are n on 2 terms in this whole series. Okay. All right, and then I can actually just rehearse what's going on because this fits exactly the pattern that I've got, and then my power here, x, is actually 2. Right, so the 2k. So I don't have a general one here. This is for, what does this represent again? How many alphabetical choices I have apart from the B. Okay. All right, now this is nice. This is good, but I haven't got here yet. I've only gone from here to this. Right? So how do I use this over here? Right?
Divide by half.
Okay, so firstly, I don't have a 2 here. So if I bring the 2 over here, it should be here. Right? So I can say this is equal to a half times. Now again, not only do I have the division over here, the coefficient over there, I also don't have x, I have 2. Right? So I'll now write this 1 plus 2. 1 minus 2. And I'll say, like, where did that come from? And the answer is from part 1. Right? Okay, now so close. I'm right there. Now I'm up to this step. You can see the half is there, the 3 is there. And then you look at this. Now this is minus 1 to the n.
Which is
Okay. Now, this is the great thing about having a proof, right? You're like, I know where I have to end. I just have to know why. You do have to justify why this is the case. Minus 1 to the n, it's equal to 1. Why on earth would that always be the case? And the answer is because I only have even powers. Like, this is the switching thing from the general solution for sine, isn't it? Right? Which always goes forward for even values. That's why we do that. So I can say that's half 3m plus 1 as this equals 1 for even values of m.